That's not what I want. So I gave the test back. The average was a 75.5 with the curve. We're not going to have a quiz on Thursday. I'm going to have it another time. It's just too soon. But anyway, so I was talking, we were dealing with effective nuclear charge last time. Which is we call Z effective. And this, as I said before, is like the charge that's felt by the outermost electrons in an atom. And the question is, why do we care about it? Why is it so important? And the reason why it is, and I will go, by the way, I'll go through what it is again, because I know I should give a little review every time. But I just want to say from the outset that this is very important because we can't really understand periodic properties without knowing something about Z effective. And what I mean by periodic properties are, we've been using this table all semester called the periodic table. And so today we're going to talk about different trends in the periodic table, different properties of atoms that vary as you go across and down the periodic table. And these properties we call periodic properties depend on the effective nuclear charge, that's the charge experienced by the outermost electrons in an atom. And in order to understand these properties, you have to understand a little bit about Z effective. So just to go over that again, this effective nuclear charge is like the charge that's felt or experienced by the outermost electrons in an atom. It's not the entire nuclear charge, because there is what we call a partial, like, cancellation of some nuclear charge because of electrons. And especially because of electrons that are actually in between one of the outer electrons and the nucleus. And these electrons, I'm going to call them the in-between electrons. And so in between a valence electron and the nucleus, all electrons screen each other, but these in-between electrons shield or screen some of the nuclear charge. So instead of dealing with the Z from the periodic table, we have to subtract a number from that to get what we call the effective nuclear charge. So this is subtracted. This is what we did last time. I had a sort of an activity where we went through doing this. And the way we did this, so this is basically the shielding term or term. And what we did last time was we made two assumptions about this shielding. Okay, the first one was that core electrons, and remember what core electrons are. When you write an electron configuration, so you have, say, sodium, let's take sulfur, and you have 1s2, 2s2, 2p6, 3s2, 3p4. And a lot of times what we do is we write it as, what would it be? Neon, argon, no, neon. Yeah. 3s2, 3p4. These are what we call the core electrons. For smaller atoms, it's just, the rare gas configuration of the previous element. later on, if you were to study this in more detail, the filled D shells would also be in there, but we don't need to worry about that because we're not talking about ones further down on the periodic table. So basically, these core electrons are in filled shells, and they are in lower shells than this n=3 shell here. So they do a really good job of screening. And what we do is we subtract all of those electrons. We say, okay, let's make the assumption that the core electrons do a perfect screening job. So we basically subtract 1 proton from the nucleus for every electron in the core. So for sulfur, this is 10 electrons. So we have 16 electrons. That's the Z, or actually Z, 16 protons in the nucleus, right? Minus the shielding. So that's minus the number of core electrons. So we have 16 minus 10, which gives us 6. So we say that the effective nuclear charge is approximately 6. The other assumption, which I've implicitly made here but didn't state, is that an electron, an outer electron here, so say one of these electrons here, is not shielded at all by its fellow n=3 electrons. So valence electrons do not shield each other at all. So that's the second assumption. Okay, that's why I don't subtract more than 10. Okay, stop at 10. So in this way, we can figure out what Z effective does as you go across and down the periodic table. So as you go down the periodic table, okay, so what we're looking at now is what is the trend in Z effective as you go down and across the periodic table, sort of the next thing we're talking about. As you go down the periodic table, you're adding whole shells. So if we take the example of the alkali metals, for example, okay, we have lithium, which is helium. What is it? Helium what? Go look at your periodic table. Lithium is Z=3. So it's helium. What comes after that? Remember, as you go across the next period, it's the next shell. So helium 2s1. Neon, I'm sorry, sodium, not neon, is neon 3s1. You go 1 down, potassium is argon 4s1. Rubidium even, krypton 5s1. So you're adding whole shells, but you have the same number of valence electrons. So if you take a look at your Z values, so here we have Z=3, 11, 19, 37 from the periodic table. And now what would the shielding be? Okay, so the shielding comes from this rare gas part of the configuration. This is 2 electrons. For neon, it's 10 electrons. For argon, it's 18 electrons. For krypton, it's 36 electrons. So if you take those numbers, you put them here, 2, you're going to cancel 2, 10, you're going to cancel 18 and 36. And now if you simply take the difference between those, so we have Z minus S, which is what we're calling Z effective. That's 3 minus 2 is 1. 11 minus 10 is 1. 19 minus 18 is 1. 37 minus 36. So to a first approximation, Z effective does not change going down the periodic table. Now, is that the truth? No. But Z, as you see, goes from 3 to 37. It doesn't change that much. Maybe it changes to maybe it's 2 instead of 1, but it's more or less, we can make this assumption in Gen Chem. So we say that more or less, as you go down the periodic table, the effective nuclear charge is approximately, that's my little approximately symbol, constant. Okay? What happens as you go across the periodic table? That's the next question. So what you're doing there is you're basically adding electrons to the same shell. And what have we already said about adding electrons to the same shell? Do they screen each other? Do they screen? If I have an electron in the same shell as, so I'm an electron in the third shell, right? Do the other n=3 shell electrons, do they do a good screening job? When do electrons do the best screening job? When they are where? When they are in between the nucleus and a given electron. So another n=3 electron is not going to screen the nucleus from me very well. Okay, so adding electrons to the same shell, the screening stays the same. Okay, because the valence electrons do a lousy job of shielding electrons from the nucleus. Electrons in the same shell do not do a good screening job. So as you add electrons to the same shell, S is about the same. The value of S comes from, like we calculated here, it comes from the previous rare gas, right? This 2 electrons is from the rare gas. 10 electrons for neon from the rare gas. S is about the same. So what happens as you go across the periodic table, Z increases, but S is the same. So Z effective increases. So the shielding is not very complete. As you go across the periodic table, you're not doing any more shielding. So the number, Z effective, simply goes up. And this is what we found. We did this exercise last time. We rushed it at the end. If you want to hand it in, I'll give you special problem credit for it. But the basic conclusion from this is that Z effective increases as you go across the periodic table. Here you have 2, 4, 5, 6, 7, etc. as you go across the periodic table. But as you go down the periodic table, Z effective is more or less the same. So it's approximately constant as you go down the periodic table, I should say. So these are the 2 conclusions. And if you have these in your mind, then you can go pretty far in understanding periodic properties. There's one more factor, however, which is easier to understand than this business with Z effective. And the other factor has to do with the value of N for the valence electrons. So another factor that's important that matters is the N value of the valence electrons. But that's pretty simple to understand, right? Because as you're going across the periodic table, you're filling the same shell, more or less. So as you go across the periodic table, N is approximately constant. But as you go down the periodic table, what happens to the value of N? What are you doing as you go down the periodic table? What's that? Yes, it goes up. And that's like if you take a look at what I showed you here, right? This is going down the periodic table, right? And you're simply adding entire shells, but you end up with the same valence, the same number and type of valence electrons, but in a one higher N shell. So as you go down the periodic table, you're adding whole shells. So N increases. So this is another important factor in determining periodic properties. And I have this picture, I don't know, this is on the handout that I gave out that's about the effective nuclear charge activity. If you turn the page, it has this picture there. And it just summarizes what I've really just said. As you go across the periodic table, the effective nuclear charge increases. The nuclear charge is increasing, but electrons are added to the same shell. So the shielding is not effective going across the periodic table. So Z increases and Z effective increases. As you go across the periodic table, the shell value stays the same. As you go down the periodic table, the Z stays about the same. And you should say, please see activity on Z effective. I changed this, but I didn't change that we did last week. And also the value of N increases. So Z stays the same, N increases. This is a mess. Okay, so if you ever just want to refer to this, you can use it. And now what I would like to do is go through the different periodic properties and talk about how they depend on Z effective and N, and how we can determine how those properties change. So the periodic properties that we're interested in periodic properties of interest are size, the size of atoms, which is like the average distance between the outer electrons and the nucleus. Ionization energy, which I'll tell you more about when we get to it, and electron affinity, which you might imagine affinity means, wanting something, an attraction to it. So electron affinity is like how much that atom wants an extra electron. Okay, so let's first do size. So this is really like an average distance from the nucleus to the outer electrons. Okay, and because orbitals are like electron cloud distribution functions, they're like electron density. You don't really know exactly where the electron is at any given moment. So that's why, we could find an average. That's what this really is, a size thing. It's not a definite thing, but it's an average distance. Anyway, the size of an atom varies with the N value of the outer electrons and the effective nuclear charge. So we want to first know, how does size depend on these two factors, N and on Z effective? So first, what would happen as the shell value increases? As N increases, the shells are further and further away from the nucleus, right? So shells get further from the nucleus. So what does that mean for the size? Yeah, okay. So size increases. Okay, so that's pretty makes logical sense. Now, what about effective nuclear charge? As effective nuclear charge increases, what does that do to the size of an atom? We're talking about the attraction of the outermost electron to the nucleus. As that increases, what's that going to do to the distance? Yeah, it's going to pull that electron closer into the nucleus. As Z effective increases, electrons are more attracted to the nucleus and are pulled in closer. So size decreases. Okay, so now with that, let's think about the trends in size as you go across and down the periodic table. Okay, so let's first, so again, we're still talking about size. What happens as you go down the periodic table? So first we have to say, what happens to Z effective? So what happens to effective nuclear charge as you go down the periodic table within our approximations? Stays the same. Let's go back. I know you said that. All these twos, right? Remember back here, we talked about how, here's Z effective for the alkali metals. You subtract out those core electrons. So going down, and also on this lovely handout here, as you go down the periodic table, Z effective stays about the same. So what does that mean for size? Well, that means Z effective, so it's about constant as you go down. So this has no effect on the size. So the only thing that matters now is as you go down the periodic table, the value of N, the shell value, increases. So what does that mean? The size increases. Okay, so for every one of these things that we analyze, one thing is going to be constant, either Z effective in N, and the other thing is going to determine the trend. So no. Well, yeah, no, it stays about the same. No, you know what? First approximation, we're not talking about then this happens and that happens. No, Let's keep it simple, Isaiah. As electrons being that it's further away, you said when it gets smaller. So now you're trying to say, okay, we have a trend here. Let's go with that. And now what does that do? Does that feed back on the Z? We can't go there. Yeah, I'm trying to simplify this a lot for you guys. I know, but let's just take it at face value, okay? Of course, it's way more complicated than this, but that's all right. What happens as you go across the periodic table? That's right. And the size stays about the same. That's right. So no effect of oh, sorry. I mean, N stays about the same. So N has no effect on the size, but Z effective increases. So this means greater nuclear attraction. Which means that the electrons are pulled closer, which means that the size decreases. So there are our trends. As you go down the periodic table, the size increases, but as you go across the periodic table, the size decreases. This is hugely unintuitive because what's happening as you march across the periodic table? What are you doing? You're adding a proton to the nucleus and an electron to the outer, you're adding both a proton and electron. And yet, even though you're adding things, the size is getting a little smaller, which is cuckoo, right? But it's because of where you're adding those electrons and the fact that the outer shell electrons do not shield each other very well at all. And so those outer shell electrons become more and more affected by that nuclear charge and get pulled closer as you go across the periodic table. So this is pretty counterintuitive. But it's true. Okay. The size decreases as you go across the periodic table. Okay, let's do ionization energy. So what ionization energy is, this is the energy that is required to pull an electron away from an atom. I believe I said last time that the dominant interaction in atoms is the attraction of electrons to the nucleus. So when you try to pull an electron away, it's being attracted to that nucleus, and so that's why it takes energy to do this. This is when we talked about the photoelectric effect. Remember, they measured the energy it takes to pull an electron from a metal surface. That's really the same thing. You're taking an electron away from all the nuclei or the nucleus that it's associated with on the metal surface. That required energy. This requires energy. So it requires energy because of the electron being attracted. Okay, so for example, if you took sodium and you end up with a sodium ion, an electron, the delta H for this process is the ionization energy, or the for sodium. Okay, and both of these are positive. It requires energy. Okay, so how would this property depend on Z effective and N? We call this IE. How does the ionization energy depend on Z effective and on N? Okay, so let's first figure. As N increases, okay, so you've got these atoms. As you increase the value, the N value of the outer shell, and we're talking about removing an outer shell electron, I should say that, to pull an outer shell or valence electron away from the nucleus. So if that electron is further away from the nucleus, it's going to feel less attraction because that attraction falls off as the distance. It decreases as you increase the distance apart. So as N increases, the electron feels less attraction. And so the ionization energy decreases. It's easier to pull an electron away from a larger value of N shell. Okay. Now, Z effective. As Z effective increases, what would you say? So now that outer electron, if it's feeling a greater attraction to the nucleus, that's going to be harder to pull away, right? As the effective increases, there's greater attraction to the nucleus. So it's harder to pull the electron away, which means that the ionization energy increases. Okay. So now let's look at those periodic trends. Okay, as you go down the periodic table, what happens to Z effective? More or less constant. N, what happens to N? Do you all agree with him? Just because I only get one answer, but it'd be nice if a few others would answer too. All right. So Z effective being constant has no effect. But the fact that N increases, what does that do? Ionization, as N increases, ionization energy decreases, right? Because it's easier to pull an electron away from a larger N shell. Okay. As you go across the periodic table, what happens to N? It's more or less constant. What happens to Z effective? It increases. So if Z effective increases, that's pulling the electron more strongly. So the ionization energy, the energy needed to pull that electron away, is greater. Okay. So that's the periodic trends in ionization energy as you go across and down the periodic table. Now for ionization energy, I'm just going to show you this. Where is it? Here. Okay, I'm not going to cover this year in Chem 104, 103. This shows you what actually happens. So this is hydrogen helium. So this is going across the periodic table. So you could see the ionization energy increases. Here's lithium to neon. I think I gave you this picture. I did, yeah. It's on this thing that has the pretty orbitals on the front. So you could see lithium to neon is going across the periodic table, and you can see the ionization energy is increasing. But what I'm not going to talk about this is these bumps in the road. There are a few little hitches where this trend isn't perfect, but for the most part, it works. These are all going across the periodic table. Lithium here, sodium's a little lower, potassium's a little low. So going down the periodic table, you do get a decrease in ionization energy. But like I said, there's bumps in the road, but we're not going to talk about those bumps. All right. In fact, then maybe I'll leave a little space for that, but those specific bumps don't matter to us. So
that last section for writing your last update. Thank you.
Okay, that's fine. So, which leaves us with one more property to talk about. And that is something we call electron affinity. And what electron affinity is, this is the energy that is released when an atom gains an electron. I guess an ion could do it too, but when an atom gains an electron. All right. So for example, if we had fluorine and an electron and we get F minus from it, okay? So this process, do you think it would be endothermic or exothermic? So if you have an electron and you have an atom over here, the dominant interaction is an attraction to that nucleus. So it would release energy because it makes it more stable to bring it together. So this process is endothermic, exothermic, duh. There we go. So it releases energy. And this is due to the attraction of the electron to the nucleus of the atom.
So it makes it more stable.
Makes it more stable, yeah. And electron affinity also depends on, guess what? Z effective and N. Okay, so let's see what happens. How does EA depend on Z effective and N? So as N increases, okay, so you're adding an electron to a shell that's further and further away from the nucleus. Does that atom want that electron more and more or less and less? Less and less. So as N increases, the electron affinity decreases. Okay, and that's because the attraction is lower when the electron is further away from the nucleus. Also, as the effective nuclear charge increases, what happens to the electron affinity? So now you have a greater and greater charge, positive charge experienced by an outer electron. That means the electron affinity would go up because that attraction is stronger. So the electron affinity increases because there's greater attraction. So this is a greater attraction. So that means more energy released, which reminds me, I didn't tell you one thing. So this is an energy release. That's is to say that this delta H, which we call the electron affinity, is negative. So when I say something has a large electron affinity, I mean that this number is more negative, that it releases more energy, okay? So a larger EA means more negative delta H for gaining an electron. Just to make that perfectly clear. All right, so now what is the periodic trend? The electron affinity trends as you go across and down the periodic table. Okay, down the periodic table. What happens to Z effective? Well, Z effective is the one that's constant. Yeah, okay. And N increases. So Z effective has no effect. Right, so as N increases, you're getting further and further from the nucleus. EA, the electron affinity, the desire for that atom to accept an extra electron decreases. Okay. As you go across the periodic table, the N value is what is about constant, but Z effective increases. So what happens to the electron affinity? It increases because there is a greater attraction, a greater experienced nuclear charge. Okay, so I do have a piece of paper here in that, I showed you this one with the trend in electron affinity. This is on the, after the effective nuclear charge activity that we did last time. And the next page has all three of these things. So I'd like you to get started on this. It's really just repeating what we just did, but to think about it. So this is basically saying, it's asking what happens to size. So you should say, because N, this is what happens to N and Z effective. And so for each blank, you should put increases, decreases, or stays the same. Okay. And I just want you to start this here and start filling it in. And to finish it at home, I'll give you a special problem credit for this. So just start it. And all the answers we've covered, but what I'd like you to do is think about it. And if you have any questions, you should ask me about it before we go on. Okay. This, yeah. I don't know if you got this. Oh, it's also. That one. Oh, no. Yeah, I got it. If you're just sitting there, some of you have finished this very quickly. The next thing I'm going to do is this. Compare the sizes of these atoms. And I'm going to show you the best way to do that. So I'd like everyone to hand in that special problem. All you have to do is fill in those blanks. We did 2 special problems for them.
Are we adding that bottom part to the special count?
No,
Okay.
no, no.
Thank
Well, we're gonna do that right now. Cool. Alright. So you get the hang of it, you're trying to think your way through this, you have any questions? All right, so I'm gonna show you how to do this. Because oh, I wasn't gonna do it yet. I'll go ahead and do it. Oh, no, I was gonna, right, I have something else to do first. I have to do this other thing first. All right, so this is where we're at right now. Let's see if I got this size right here. Yeah, I gotta make this a little smaller. Okay, so here's the thing. Let's focus on the top part of this handout right now. As you go across the periodic table, we have these trends. We have an increase in ionization energy. It's harder to pull an electron away. We have an increase in the affinity of an atom for an electron and the desire to accept an extra electron. So it's easier to add an electron. Size decreases as you go across the periodic table. As you go down the periodic table, if you notice, the trends are exactly the opposite. So how about if instead of thinking about this trend going down the periodic table, we flip it and we say, so going up the periodic table, everything becomes opposite, right? It becomes harder instead of easier to ionize an electron. It's easier instead of harder to add an electron, and the size would decrease. Now, why on earth would I do this? The reason why is to confuse you. No, it isn't. It's so that I can draw a continuous arrow, right? Because it doesn't really help to draw a continuous arrow if I have one trend going down and another trend going across. I want to go up and across and up. That means that in the direction of the large blue arrow, right? And also, of course, be going up, even in the middle of the periodic table. But mostly, if you go up and across, it's the same trend. And and what it means is the ionization is increasing along these blue arrows, right? Electron affinity is increasing and size is decreasing. So that's why I flipped them. So you can think about it as continuous change as you go in a certain direction on the periodic table. You could make it a continuous arrow. So, so here's the thing. I told you I'm going to show you the easy way to do this, to compare sizes. Okay, so the atoms that I wanted to compare the sizes of are sodium, aluminum, nitrogen, phosphorus, oxygen, and rubidium. So the easiest way to do this is to circle these on the periodic table. Here's aluminum, nitrogen, here's oxygen, here's phosphorus, and here's rubidium. And remember, we have this big arrow that goes this way and increases in ionization energy, increase in electron affinity, and decrease in size. So as you go up, you're decreasing the size. So here you're going up, here you're going across, here you're going up and across. And you see that in the direction of the arrows that I have drawn, size decreases. Notice you don't have anybody out of line. Like I didn't give you one over here, which would be hard. I won't ever do that. I'll always give you ones that you can figure out. So size decreases along, going up and to the right on the periodic table. So that means size decreases from rubidium to sodium to aluminum to phosphorus to nitrogen to oxygen. So that means that size increases in the opposite order. So oxygen will be smaller than nitrogen, which would be smaller than phosphorus. So that is an easy way to determine trends, is to use the fact that you have these changes in a very understandable way as you go across and up the periodic table, and to arrange the atoms. Maybe not dirty a copy of the periodic table every time, but you can at least look at a periodic table, see where the atoms are located. Are you raising your hand? Can you speak up? Oh, Well, you got a gotcha right there. All right, great. Okay. Good. Thank you for pointing that out.
I don't understand that.
No,
So like go this way.
to the right.
Yeah, so like you started at rubidium, and went to sodium,
Well, I went up.
went over to and then phosphorus.
Yeah. So I'm always moving to the right or up. I have to go up to get to nitrogen, but I want to move up or to the right. If I move up or to the right, I know that size decreases. So you could do that with this could use this method with any of these things, really. With any of these trends, as long as you know that if you go up and across, the trend stays the same. And you have to look at which way it is changing. And then
So if
You-
you go across and then up, it's still decreasing.
yeah, if like say I didn't give you rubidium, I started with sodium, you would just go across. And then you would go up from P to N and across from N to O. So as long as you're going in the up or across direction, the trend is not changing. Size is decreasing. Or the ionization energy is increasing, or the electron affinity is increasing. So anyway, that's a very good way to do to answer those types of questions. Okay. By the way, did you see that I posted chapter 6 homework? I did that before the weekend.
And yeah, there's some trouble
On where that what?
on the homework.
Oh, yeah, there's all kinds of stuff on this, yeah. All right, so that means that this red circle in the upper right of the periodic table, this has the elements that have the highest activation, that have the highest electron affinity, the highest ionization energy, and the ones in the lower left have the lowest electron affinities and the lowest ionization energies. In fact, this kind of whole idea of these trends across the periodic table will help us really get a better idea of the distinction that I made at the very beginning of the term between metals and nonmetals. Okay, so let's think about that for a minute, because we know the metals are on the left side of the periodic table. On the left side of the periodic tables, and metals have, okay, so what do they have? They have low ionization energies. How do I know that? Because ionization energy increases as you go across the periodic table. So on the left side, the ionization energy is low. They also have low electron affinities. So what that means is low ionization energy means not too much energy is needed to ionize. In other words, to lose an electron. Low electron affinities means they don't really want an extra electron. Not much energy is released. On gaining an electron. And what do you know about metals? What do they form? Well, they don't form ionic compounds by themselves. Which part of the ionic compound do they form? What sort of ions do they form? They form positively charged ions, cations. How does this go with what we're talking about here? When you form a cation, you're pulling an electron away from an atom, all right? For metals, it doesn't require that much energy to do that. because they're on the low ionization energy side of the periodic table. So they more easily form cations. Would they form an anion? Their electron affinity is not very high. They don't, not much energy would be released if they formed a cation. So basically metals tend to form positively charged ions because of their low ionization energy and low electron affinity. So on the other side of the coin, let's look at the nonmetals. And nonmetals have, because they're on the right side of the periodic table, they have high ionization energies. So what that means is it's very hard to pull an electron away. That does not bode well for forming a cation. And they don't form cations, right? They form anions. They have also got high electron affinities. They release a lot of energy when an electron is added. They get a lot more stable when adding an electron. And this makes a lot of sense, right? Because when they form ions, because nonmetals can also be involved in covalently bonded molecular compounds, but when they do form ions, so when nonmetals form ions, what type of ions do they form? What? Anions, negatively charged ions. And that's because they have high electron affinities and they don't lose electrons because they have high ionization energies. Okay. So basically what we know so far, and we know actually part of this from the very beginning of the semester, is that when metals form positive ions, they end up with the rare gas configuration. Do you know what I'm talking about there? I'm talking about if you have sodium, 1s2, 2s2, 2p6, 3s1. Is that right? No, yeah, that's right. So that's sodium. Anybody got a periodic table? I think it's argon, right? Oh, here it is. Neon, yeah. Neon, 3, oh, is it? It's in the third period, right? Yeah. Okay. So we knew we didn't know about 3s1, but we knew, remember that when a metal loses an electron, it goes to the previous rare gas. It needs to lose one electron to get to the previous rare gas. That's what we learned about at the very beginning of the semester. But now we know that it's losing this electron to become sodium with just the rare gas configuration. That in general, metals tend to lose the number of electrons so that they attain a rare gas configuration. When they form positive ions, they form the rare gas configuration. Magnesium, which is neon 3s2, loses 2 electrons to form Mg2+, which is just the rare gas configuration, right? Etc. Okay, so metals tend to form positive ions with a rare gas configuration. We also know that so you might ask this question: why do metals stop at the rare gas configuration? It all comes down to that, but let's talk about that further. Why? Okay. Most things, it comes down to energy. So I'm going to use magnesium as an example. And I'm going to give you some energy information. And I'm going to show you why magnesium stops at +2 and doesn't go on to form, say, a +3 ion. Okay, so let's take magnesium. And if we ionize magnesium, so we take an electron away, the delta H for this process, which we call the ionization energy, is 738 kilojoules. Okay. Now, let's think about taking that second electron away. So now we have the magnesium single plus charge. And now we take away a second electron. So this becomes Mg2 plus. And the ionization here, energy here, is 1450. So here's my question, first of all. Why is that number 1450? Why does it take more energy to pull the second electron away than the first? About the same distance away, right? Because they were both in the same end shell. The attraction. Remember, negative charges and positive charges are attracted. When you lose an electron, now you have a positive ion. That positive ion is holding an electron much more strongly because of the fact that you have a 2+ charge on that ion. So it's expected that it takes more energy to pull the second electron away. But here's the really amazing thing. If I take magnesium 2+ and I pull off another electron, this is what happens to the ionization energy. So look at this. Here you have a certain ionization energy for the first process, 738. Then it doubles, right? It goes up to 1450. This is like, so that's a doubling. Here, it multiplies by a factor of 5. So this is a huge jump in energy that's required to pull the third electron away. So here's the question: why does it take so much energy to pull the third electron away? Okay, and so look, it helps to think about electron configurations. We know what magnesium's configuration is. Okay, when we lose an electron, you take the last valence electron away, you get 3s1. When you take away the second electron, you have a nice rare gas configuration. If you try to take the third electron away, it's going to have to come out of that rare gas configuration, out of that core, and you'll end up with 2s2, 2p5. So apparently, it's extremely hard to remove an electron from the rare gas configuration or the core electrons. And that's why it never happens. It just costs too much energy. But why is it that it costs so much energy? What is it about these core electrons? So now think about it. These core electrons fill the n=2 shell. So if you start taking away an electron from the core, right, you're removing an electron from a lower value of n shell, which is closer to the nucleus and more tightly held. So it's more tightly held. Also, let's not forget that you're trying now to pull an electron away from an ion that's already got 2+ charges. That's a strong attraction, plus minus attraction. Okay, so you're trying now to pull it from a 2+, so it's more tightly held in the n=2 level or shell. That's one thing. And now you're trying to remove an electron from a +2 ion. And of course, electrons are attracted to positive charges. So due to the attraction, to the plus minus attraction, this is really very, very hard. Okay. So metals stop losing electrons when they reach that rare gas configuration.
So my brain understands, like, when you're talking about the third electron, the chances of that happening in the natural world are slim to none.
Yeah, so in other words, I know that energy because some guy, some scientists shot a laser on that thing and sort of forced it to figure out that energy difference. Okay, so the table I'm going to show you here, which you have in this packet, I think brings this point home very well. Of course, it's like a mile away, but here it is. All right, so what we've been looking at is this part of the table, magnesium. And these are the numbers I gave you, 738 to remove the first electron. We call that the first ionization energy. This is to remove the second electron. We call it the second ionization. Not too bad, you know, but here is that big jump. So the dotted line marks this big jump and what happens to the ionization energy is you try to remove a third electron from magnesium. Now, with sodium, the big jump happens here between the first and the second, because sodium only has one valence electron. Okay, so here you're trying to remove from the core. So here, so the big jump in energy corresponds to removing a core electron. So for sodium, the big jump is going to happen after the first electron is removed. Right, because it only has one valence electron. For magnesium, it's going to happen after you remove the first two. Aluminum, it's going to happen after the first three. So you see the big jump is over here between the third and the fourth. It goes, look at that. From 2,700 to 11,000 is a huge jump in energy to remove an electron from the core. So big jump in energy corresponds to removing core electron. Core electrons are in lower n values. They're tighter held to the nucleus. And you're trying to remove electrons from successively more positively charged ions. And it's just not going to happen out there, as she said, in the real world. So basically, the conclusion is that metals stop losing electrons at the rare gas configuration. So, all right, so what about nonmetals then? What do they do? I really would like it. So what about nonmetals? Why don't they gain more electrons after they achieve the rare gas configuration? So they've already gained electron. They're in the rare gas configuration. why don't they gain more electrons, So for example, geez, I really need a periodic table. Fluor. Oh, kind of, not really, but yes, close enough. So fluorine is 1s2, 2s2, 2p5. That's fluorine, neutral, sorry. Oh, yeah. So F minus is 1s2, 2s2, 2p6, which is neon. Okay. Oxygen. Uh, oh. So O2 minus would be 1s2, 2s2, 2p6, or neon, and it stops gaining electrons. Here, fluorine stops after 1. Okay, so the question is, why? So you have to think about it. After a nonmetal gains the number of electrons it needs to get the rare gas configuration, where would the next electron go? So it would have to go into a shell with a higher value of N, okay? And those higher value of N shells don't have as strong an attraction to the nucleus, so it wouldn't release as much energy to absorb an electron into one of those shells, okay? It would go into a higher N value shell, which is not going to be attracted as strongly. And also, remember, once you have that rare gas configuration, that atom has already gained 1 or 2 or even 3 electrons. And so you would be, you would be adding an electron to an anion. But negative charges repel, right? So this is not going to be easy. It's not going to release so much energy. So a negative ion has a tough time attracting electrons, especially when they're going to go into the next shell. So basically, nonmetals stop gaining electrons at the rare gas configuration. So I don't know what any of you might have studied in high school, but I know that when I was in high school, a long time ago, teachers would say that the atom gets to the rare gas configuration because because that's what all atoms want to be at, is a rare gas configuration. Like they put a human desire on it or something, which really, it's really all about energy. How much energy is it going to release? How much energy is it going to cost to do a certain thing? And so the rare gas configuration is it. It's really based on energy. And also for nonmetals are involved in many, many compounds that are not ionic compounds, but they still sort of share electrons to try to get a filled shell, try to get a rare gas configuration. So nonmetals use covalent bonding or sharing electrons to attempt to get the rare gas configuration by sharing electrons. which we are really just about to get to. In fact, we really have kind of just segued into chapter 7. Okay. And before we start to talk about covalent bonding, which is really what we're going to talk about next, chapter 7, I need to tell you about this property called electronegativity. How many of you have heard of that, like from high school or somewhere else? Yeah. Electronegativity. So what electronegativity is the ability of an atom to draw electron density to itself. And what I mean by electron density is like to sort of pull that electron cloud over towards where it is. And electronegativity, this ability to pull electrons towards an atom depends on all of these properties. So electronegativity, which I call En, is really based on all these properties that I've been discussing. Z effective, N, ionization energy, and electron affinity. And I'm not going to tell you the formula that they use to calculate an electronegativity value, but basically electronegativities are associated with, so the higher the Z effective, the higher the electronegativity. So let me write this down. High electronegativity is associated with these things: large effective nuclear charge, smaller values of N, large ionization energy, and large electron affinity. Okay, so if you have a larger value of the effective nuclear charge, that means there's a greater nuclear attraction. I call it nuclear pull on the electron. Small n means you're closer to the nucleus, so there's a greater pull. Large ionization energy means it's hard to remove an electron, means that atom wants to keep its electrons. Large electron affinity means an atom wants to gain electrons because it increases stability, releases a lot of energy. So this electronegativity is based on all these things that we've talked about. And if you think about this, we had our periodic table and we use these arrows in this direction. So this is going to higher, larger ionization energy, larger electron affinity, higher electronegativity. Okay, so these same arrows you can use for electronegativity, except one thing I do want to mention, that you have to leave the rare gases out. And if you look at the handout that I gave, you could see that last column, let me see if I can show it to you, because I didn't point it out at the time because there were too many other things to talk about. So these blue arrows here, notice I have a column here for the rare gases. And while the size and ionization energy trend continues through the rare gases, the electron affinity trend stops. That is to say, a rare gas does not really want extra electrons. So the trend really stops before the rare gases. And the same is true for this electronegativity. So leave out the rare gases. They are not very electronegative atoms. They're not even involved in most chemical they don't have a lot of chemical reactions because they like life just the way it is. They're very happy. I don't know, maybe they think they live in Florida or something. Everyone always seems to want to move to Florida. I wouldn't move to Florida if you paid me, but that's anyway. Okay, so this is the electronegativity charge. And I will always give you this chart. This is not something you have to memorize at all, but you could see the trend here. You're starting at 0.7 in electronegativity. And as you go up, so in this direction, you're increasing electronegativity. Lithium is 1. But and as you go across the periodic table, these numbers are getting higher. Hi. So the numbers are increasing like this and like this. And notice there's no rare gases here. That's not included. All right. So we are going to talk about covalent bonding very soon. Okay. And covalent bonding involves sharing electrons between two atoms. So in covalent bonds, why does it take so long to erase? In covalent bonds, electrons are shared between two atoms. Okay, and it's the electronegativity values for each atom that tells us if the sharing is relatively equal, or if one atom is sort of pulling more of the electron density towards itself. So it's the difference in electronegativity values tells if the sharing is sort of equal or not. Okay, so let me give you an example. Sort of classic example here is the water molecule, H2O. Okay, so this is the water molecule. Here's 2 bonds. I'm going to talk about how we draw these structures for water and other atoms soon, molecules soon. But what I want to do is do a little bit of a calculation. I want to calculate the difference. That's what this means, difference in electronegativity between H and O. Okay, so go ahead on your electronegativity chart. We're going to consider the OH bond and look up the electronegativity of oxygen and the electronegativity of hydrogen. And what do you get for a number when you do that? That's 3.5, and hydrogen 2.1. And oxygen is way over on the right side of the periodic table. Hydrogen is way on the left. So it's no surprise that oxygen has a greater electronegativity. It has a greater tendency to pull electrons towards it, right? As an atom, it sometimes forms a negatively charged ion. That's how much it likes extra electrons, right? But if you take the difference here, and you're always going to subtract the smaller number from the larger number. We don't have plus and minus delta EN. So delta EN is just the larger minus the smaller, whatever order it's in. And it comes out to 1.4. And so now, what does that mean that you get this difference of 1.4? Does that mean there's equal sharing, or does it mean there's not equal sharing? So that's the question. So is the sharing of electrons between H and O equal or not? It's actually not, but let me tell you how we interpret this and what it means. So, okay, so we have these guidelines about differences in electronegativity. If the difference in electronegativity is 0.4 or less, so less than or equal to 0.4, then we say the sharing is relatively equal. Okay. if the difference in electronegativity is 0.5 or more, then it's not equal. So I'm going to come back and write a few more things here, but I want to show you how we indicate this on a bond. It would move. So say we have, or on in a molecule, each of these bonds. So if the sharing is not equal, what it means is that one atom, and that's the one with the larger electronegativity, is pulling the electron density closer to it. And when it does, it acquires something of a negative charge. So we would write a delta negative over here. The more electronegative atom acquires a partial negative charge. We call it delta negative because this delta means small. So it's a small negative. And the hydrogen, each one, would have a slight positive charge. And we say that the OH bonds are polar because there's this difference. You know, one of them has more electrons, the other one has fewer. So one has a slight negative charge, one has a slight positive charge, and we call those bonds polar.
Use of delta here. So we had delta H and delta N before we were using a triangle symbol. Why is the symbol different now? For delta.
The delta indicates the charge. This big delta is the difference in electronegativity.
Right.
The difference in electronegativity is what gives rise to these small charges. The delta here doesn't mean change, it means small.
Okay.
Yeah.
What I'm actually referring to is the symbol itself.
Yeah, it's a little stupid and confusing, but I didn't make it up.
Okay.
Yeah, this is a capital delta and this is a small delta. But it's great when you go to Greece, then you could read the signs, you know, that's a D sound. So you can sort of sound out all the signs without knowing what the hell they mean. It's pretty funny anyway. All right, so getting back to this. All right, so we have these delta charges that make certain bonds polar because the electronegativity of different atoms is not the same. So an OH bond has an electronegativity difference of 1.4. That's pretty big. That's a pretty polar bond. That's a pretty big difference. So that's a quite polar. No, the electronegativity is between two atoms in a bond, two at a time. So you wouldn't be multiplying anything by two here. No, it's just a straight difference. Okay, so this is a page. What the heck is this? Maybe it's the next page. Yeah, hopefully. Yeah, so this is something that comes out of the book. Oh, I don't know how that happened, but it happened. All right. So I want you to take note of a difference between myself and this OpenStax book. Sometimes that book is really stupid. But anyway, my convention, and this is what most chemists use, is if the electronegativity difference is 0.4 or less, that we say that the bond is nonpolar. And the book uses the term pure covalent, which is honestly, just nobody says that anymore. So just say nonpolar. if it's 0.4 or less. They think it has to be less than 0.4, and I disagree with them on that. So use mine, because that's what I'm going to, that's how I'm going to grade things, okay? If it's between 0.5 and 1.8, so in other words, instead of being between 0.4 and 1.8, as it says here, it's between 0.5 to 1.8. We say that it is a polar bond. And if it's greater than 1.8, we call it ionic. Okay. We're not going to run into much of that. Okay, so these are the terms I use. Nonpolar. I mean, it says, I say either phrase is fine because I'm trying to be diplomatic, but you should understand both terms. Really, I use nonpolar and polar. So those are the ones that perhaps you should use. So let's take a look at some examples. And how about if you do this? Let's look at a CH bond. A CO bond. An NH bond. And an OO bond. Okay. And I'd like you to calculate the difference in electronegativity. Okay. And then say whether it's polar or nonpolar. And also which atom would get a delta negative and which would get a delta positive if the bond is polar. So all you need is your electronegativity chart. And I have a small one on the front page, but I have a nice big one on the next page. Finding it hard to see, which it really is okay. You can see it, but this one is even better. Okay. And so just look up those electronegativities. You could put deltas on here if you have delta charges. If you don't, then you don't put any delta charges. And that's all. No.
No.
Well, I should, you know. So, you know, we're not going to have a quiz Thursday. Did I say that already?
We didn't, but thank you.
Yeah, it's too soon. It's we're gonna do something. This is chapter 7. Yeah, it just didn't make sense to have a quiz when we just didn't even cover one chapter last, yeah, so. Where the delta charges would be if there are any. I don't know, I did these from memory, so now I have to check to see if those numbers are right. Oh, yeah. Good, I trust you. Okay. Everyone agreeing with me on this? So what does that last one tell you, you know? Oh, right? So whenever you have two of the same atoms, obviously, you don't have any atom favoring, pulling electrons more than the other. So any, we call them homonuclear diatomics, like F2, N2, Cl2, they'll all have zero difference in electronegativity, and they will all be nonpolar. So that one's pretty much a given. There's no delta charges there. CH bond, this is the reason why I changed the cutoff, because a CH bond is not considered polar. And with this stupid book, it would consider every CH bond polar, which is just completely wrong. I don't know how they could get away with this year after year. But anyway, our polar bonds here are the CO and NH bonds. And the one that has a greater electronegativity, which is the O here, and is the N here, is the one that gets the delta negative charge, and the H would be the other one here. And a lot of times what we do is we use an arrow and we point to the negative one. And we call this a dipole. So a dipole is just, it shows the direction that an electric field vector would point. It points from the positive to the negative. Yeah.
You said that not every CH bond.
No, they're all nonpolar,
Say about
because the book is too stupid to recognize that. And so its criterion makes a CH bond polar, which is just not something you should ever think about. It's just wrong. I don't know. Anyway, it's really very, yes, it points from the plus end to the negative end. And a polar bond has a dipole. It's just a statement of the fact that it doesn't have an even distribution of charge. And the dipole is the arrow that points from the plus to the negative. Okay. So does this make sense to everybody? All right, so I want to just tell you a little bit about covalent bonds. So these covalent bonds occur between two nonmetal atoms, although you can also have metalloid. And it's another way of having an atom attain that rare gas configuration. So like I said, it involves sharing electrons and doing it in such a way that each atom can attain a kind of rare gas configuration. And so if I just show you with hydrogen, so I could draw a hydrogen with its electron as a dot. Okay, so it has hydrogen has one electron, one valence electron. It's also one electron. And in the end, they come together. And you can think about those electrons. You could think about the two electrons as going with each one, like one at a time. right? So that's like each hydrogen now has 2 electrons. So you can say that each one has a filled shell, because for hydrogen, it's the n equals 1 shell, which only needs 2 electrons to be filled. Yeah. And this is the shared pair of electrons, which we draw as a line, which represents a bond. So we would draw this simply like that, H, H dot dot H, or HH. So this is the shared electron pair. Now, electrons in a bond, by the way, this is like he actually asked me, this is called the Lewis dot structure for H2. And this guy, G.N. Lewis, lived, believe it or not, he's from Massachusetts, Weymouth, Massachusetts. He was born in 1875, and he came up with this way of representing simple molecules using what we call Lewis dot structures, where the lines represent bonds. And okay, and so in this Lewis theory, electrons involved in a bond are at a lower energy than they were as separated atoms. So why might you think that would be true, that electrons in a bond? Well, that's like saying the same thing. Like, why are they more stable? They are more stable, but that's what that means. But why would they be more stable? Well, remember, this is what you have at first, 2 hydrogen atoms. That's not floating by itself either. And now you have a bond representing 2 electrons here that are shared by 2. So I think the bottom line is that in a bond, those electrons are now attracted to 2 nuclei. So there's greater attraction than to just 1 nucleus, right? So the electrons in a bond, I'm sorry you didn't like what I wrote there, in a bond are attracted to both nuclei. Okay, and also this gives each atom a kind of a rare gas configuration, which we've already talked about why that's particularly stable for atoms. Okay, so that was the idea. Okay, and I think I'm going to end class here. I want to just say that we're going to skip section 7.1 on ionic bonds, because we spend too much time, a lot of time early in the term, talking about ionic compounds anyway. So we're not going to cover that in this class. We'll start in with some covalent bonding next time. We'll do some Lewis structure. I did post the chapter 6 homework. It's been up for a while. Take a look at it, do it. There's not much math, just a lot of questions.
Birds.
Words, 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 I know.
Birds.
Somebody's giggling. Yeah, right.
Look at that.
Thank you. was everything I put away.
Said both of these were special ones.
This one was due today, but that's fine. Okay. I fell from my kitchen floor. It was a million things. I made 2 turkeys. Leftovers we made. And we eat a lot of turkey, and also my family really mostly likes the dark meat, so I always make extra turkeys, and then I use the white meat in like casseroles. Stuff in the kitchen, it's gonna go out on Saturday morning. And yeah. It's just like getting sore today. I'm okay, I didn't twist anything, I squat, I just, you know. Yeah. They'll appreciate it.